93 million miles is the distance between the Earth and Sunday. 238,000 miles is the distance between the Earth and Moon. These figures, seemingly arbitrary, are fundamental to configure the delicate balance that sustains life on our planet. The precise position of Earth within the solar system is not a coincidence. In our solar system, Earth's orbit around the Sun places it in the habitable zone, a narrow region where temperatures allow the existence of liquid water, an essential ingredient for life. Even slight variations in the distance could lead to drastically different results. If Earth were only 5% closer to the Sun, temperatures could reach levels where the oceans evaporate, transforming our planet into a scorching desert. Conversely, if Earth were 5% further from the Sun, our world could be a frozen wasteland incapable of harboring liquid water. The gravitational force of the Moon stabilizes the inclination of the Earth's axis, which in turn regulates our climate and the seasons. This intricate dance of celestial bodies creates an environment in which conditions remain stable and predictable, an environment in which life can thrive. If the Moon were significantly further from Earth, its gravitational influence would weaken, leading to an unstable axial tilt and chaotic climatic variations. Without this stability, the seasons would become extreme, which could prevent the development of stable environments necessary for complex evolution. At 444 million kilometers from Earth, we find Jupiter, this giant planet that acts as a cosmic shield for Earth. Its enormous gravitational field captures or deflects many comets and asteroids that could otherwise impact our planet. Without its enormous gravitational presence, the inner solar system will be bombarded by asteroids and comets, which could lead to devastating impacts. These events could alter planetary systems, modifying their composition and dynamics in unpredictable ways. If we expand our vision further, we see another layer of precision. Our solar system is located in a relatively calm and stable region of the Via Láctea, far from the chaotic and dangerous central regions, where supernovas and black holes predominate. Music. This location within the galactic habitable zone protects us from excessive cosmic radiation and gravitational disturbances, allowing the solar system to maintain its structure and, on a much larger scale, for the universe itself to function according to finely tuned physical laws. Let's consider the force of gravity. If gravity were slightly stronger, the stars would burn much faster, depleting their fuel before having the opportunity to form planetary systems. The rapid collapse of matter would lead to a universe dominated by black holes and neutron stars, leaving little room for the diverse cosmic structures we observe. On the other hand, if gravity were weaker, matter would not clump together efficiently, preventing the formation of stars and galaxies. The masses of subatomic particles, such as protons and neutrons, are also precise. If the mass of a proton were slightly different, the balance between protons and neutrons in atomic nuclei would be altered, affecting the stability of atoms. For example, if protons were significantly heavier, they could disintegrate more rapidly, leading to the instability of matter itself. Conversely, if neutrons were lighter, atomic nuclei would not hold together, preventing the formation of the elements essential for the development of stars and planets. All other constants and laws of our universe are also fixed at values that allow the formation of galaxies, stars, and planetary systems. Even a slight change in any of these values would lead to a very different universe than the one we inhabit, a universe that could lack galaxies, stars, planets, and the complex structures we observe, a universe without the delicate balance necessary for the emergence of life, a universe without us. So, how did this intricate balance arise? What is the origin of these precise configurations that govern the solar system, the galaxy, and the entire universe? Are these perfect conditions the result of chance, an inherent necessity, or some underlying design? Underlying design? Could this fine-tuning be pure coincidence? Or does it suggest a deeper and more meaningful order in the cosmos? Music. 138 billion years ago, the universe began with a minuscule point, so small that if you tried to measure it, You would need a ruler so precise that it could count the hairs on a bacterium. Imagine holding a speck of dust on your fingertip and shrinking it until it is 1 billion times smaller. Even so, it would not approach the scale of a singularity, but contained all the energy, matter, and potential of the entire cosmos. In this minuscule point resided the seeds of all galaxies, stars, planets, and life itself. The singularity was not only minuscule, but also unimaginably hot and dense. It was so incredibly hot that temperatures reached trillions of degrees. The heat was so intense that atoms did not exist, not even protons and neutrons, which melted into a hot, dense soup of fundamental particles and energy. If you could somehow withstand the heat and observe this singularity, you would see nothing solid or familiar, just a blinding, seething cauldron of raw energy and primordial particles. In terms of density, the singularity was a place where all the concepts of density we know collapse. In fact, the density was so great that the fabric of space and time itself curved to an infinite degree. Matter and energy were so tightly packed that the laws of physics, as we know them, could not even describe the conditions. This tiny, incredibly hot and dense point marked the beginning of everything. It was the ultimate paradox, a point of insignificant size, but of infinite importance in terms of potential, since in that small, incomprehensible point everything was waiting to begin. But this singularity was also incredibly unstable. The immense density of energy and the extreme temperature meant that it could not remain in that state for long. Then, in an instant, this instability triggered the expansion that we now call the Big Bang. Contrary to its name, the Big Bang was not an explosion in space, but an explosion of space. The universe itself began to grow from this initial point, and with it, time began. It was a rapid expansion in which space itself stretched and expanded, carrying with it the primordial particles and energy, but the Big Bang was only the beginning of the story. Almost immediately after the Big Bang, the universe experienced an even more extraordinary phase of growth known as cosmic inflation. This period of inflation lasted only a fraction of a second, but it had profound effects. The process of cosmic inflation can be compared to inflating a balloon, in which small bumps and imperfections on the surface are smoothed out as it inflates. Similarly, any initial agglutination or irregularity in the early universe stretched, giving rise to the smooth and homogeneous cosmos that we observe today. This smoothing effect was not just random luck, but a precise and incredibly delicate process. Let us consider the expansion speed of the universe during this inflationary period. If this speed had deviated even by a minuscule fraction, the consequences would have been catastrophic. For example, if the expansion speed 1 second after the Big Bang had been lower, the universe would have collapsed before it had the opportunity to expand. On the contrary, if the speed of expansion had been greater in the same fraction, the matter would have spread too quickly, preventing the formation of galaxies, stars, and planets. Later, as the universe continued expanding, the fundamental forces began to differentiate from each other. These include gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The intensity of these forces had to be adequate for the universe to develop as it did. For example, if the strong nuclear force were slightly weaker, atomic nuclei would not remain united, and atoms as we know them would not exist. If it were slightly stronger, stars would be consumed too quickly, preventing the long-term stability necessary for life to evolve. During these early stages, fundamental particles such as quarks and electrons began to form. These particles combined to create protons and neutrons, which then fused to form the first atomic nuclei in a process called nucleosynthesis. The proportion of protons and neutrons at this stage was crucial. If there had been a significant imbalance, the universe would have been dominated by hydrogen or helium, preventing the formation of heavier elements essential to life. This period of nucleosynthesis lasted only minutes, but laid the chemical foundations for everything that followed. As the universe expanded, it reached a critical point known as recombination. During recombination, protons and electrons combined into neutral hydrogen atoms. This process allowed photons to travel freely, leading to the release of the cosmic microwave background radiation that we still observe today. At that time, the universe also underwent a cooling process. The rate at which the universe cooled was vital. If it had cooled too quickly or slowly, it would have disrupted the formation of atoms and the subsequent development of cosmic structures. As the universe expanded and cooled, it eventually reached a point where electrons could combine with nuclei to form neutral atoms. This occurred approximately 380,000 years after the Big Bang. The timing of recombination was crucial. If it had occurred too early or late, the distribution of matter and radiation in the universe would have been significantly different. Before recombination, the universe was opaque because free electrons scattered photons or particles of light, preventing their free travel. After recombination, photons were able to travel unhindered, leading to the release of cosmic microwave radiation. The CMB offers a snapshot of the early universe, showing small temperature fluctuations that correspond to the seeds of future galaxy formation. The uniformity and small variations in the CMB temperature are a testament to the delicate balance achieved during this period. After recombination, the universe entered a period known as the Dark Age, which lasted until approximately 150 million to 1 billion years after the Big Bang. During this time, there were no stars or galaxies, and the universe was filled with neutral hydrogen. The cooling rate and initial density fluctuations, both vestiges of inflation, were eventually balanced to allow gravitational forces to amplify these fluctuations, eventually leading to matter collapse and the formation of the first stars and galaxies. If the density fluctuations had been greater or smaller, the universe's structure would have been very different. Little by little, the small fluctuations amplified by gravitational attraction began to collapse, forming the first stars and galaxies. This period is known as the era of reionization, as ultraviolet light from the first stars ionized the surrounding gaseous hydrogen, making the universe transparent to ultraviolet light. The timing and intensity of reionization were fundamental in shaping the development of large-scale structures. Dark matter, a mysterious form of matter that does not emit light or energy, played an important role during this period. Although invisible, dark matter exerts gravitational forces, and its presence acted as scaffolding for visible matter. Without dark matter, galaxies and larger structures might not have formed as they did. The precise distribution and amount of dark matter were essential for the universe's structural evolution. Dark energy, another mysterious component of the cosmos, began to influence the universe's expansion in its later stages. Dark energy is a force that drives the accelerated expansion of the universe. Its influence has increased over time, shaping the expansion rate of the universe. The balance between dark matter and dark energy is another example of fine-tuning. If dark energy had been stronger or weaker, it could have prevented galaxy formation or caused the universe to expand too quickly for structures to hold together. The period known as cosmic dawn marks the formation of the first stars. Matter clumped together under gravity, leading to the birth of stars. The perfectly adjusted force of gravity allowed these stars to form. If gravity were slightly weaker, matter would not have clumped together, and stars would not have ignited. If it were stronger, the universe might have collapsed before the stars had a chance to form. These early stars experienced life cycles that included supernova explosions, scattering heavier elements throughout the universe. These elements are crucial for planet formation and, ultimately, for life. The stars gravitated towards each other, forming galaxies. The formation of galaxies required a delicate balance between the gravitational forces and the rate of expansion of the universe. The Hubble's law, which describes the speed at which the galaxies move away, plays a crucial role in understanding this balance. The Hubble's constant, which measures the speed of this expansion, is another example of precise adjustment. If the rate of expansion were different, the galaxies might not have formed or the universe might have expanded too fast for life to develop. The clusters of galaxies, large groupings of galaxies formed in specific conditions. The cooling of the universe, the density fluctuations, and the influence of dark matter contributed to the formation of these clusters. The precise balance between the gravitational forces and the speed of expansion was necessary for the clusters of galaxies to form. Our local group, the cluster of galaxies that includes the Milky Way, is a result of this delicately adjusted process. The formation of the Milky Way was a complex process influenced by the collapse of gas clouds and the rotation, as well as the role of dark matter halos. The specific conditions that allowed the Milky Way to develop its spiral structure and habitable zones are examples of conditions inside the Milky Way. The solar system was formed in very particular conditions. A protoplanetary disk, the role of the supernovas in the formation of heavy elements, and the stability of the Sun contributed to the formation of the solar system. The stable production of the Sun, the position of the solar system inside the Milky Way, and the specific conditions that led to the formation of the planets highlight the adjustment necessary for our existence. The formation of the Earth required the accumulation of planetary material, the presence of water, and the role of the Moon in the stabilization of the inclination of the Earth, the adequate distance to the Sun inside the habitable zone, the presence of a magnetic field to protect it from solar radiation, the role of Jupiter in the protection of the Earth against the impacts of asteroids, and the adequate atmospheric composition for life are examples of the fine adjustment that made the Earth a habitable place for life. The appearance of life on Earth depended on a precise set of conditions. Liquid water, adequate chemical elements, and a stable climate were essential. The formation of complex organic molecules and the development of ecosystems sustaining life required a finely tuned environment, from unicellular organisms to complex multicellular life. The evolution of life involved genetic mutations and processes of natural selection that were only possible in a finely balanced environment. Why do stars burn at the perfect rate? Why do atoms form as they do? Why didn't the cosmos collapse shortly after the Big Bang? These are some of the questions that have led to the intriguing concept that the universe is finely adjusted. Music, the idea of fine adjustment, suggests that the universe's constants and fundamental quantities are precise shortly after the Big Bang. These are some of the questions that have led to the intriguing concept of the finely adjusted universe. Music, the idea of fine-tuning, suggests that the constants and fundamental quantities of the universe are established with such precision that they allow for the existence of life. Think of it as tuning an old radio. You need to adjust the dial exactly to tune in the station, and if you deviate a little, you only hear noise. Similarly, if the universe's parameters were slightly different, life, as we know it, would be impossible. This concept took root in the mid-20th century thanks to physicist Fred Hoyle's work in the 1950s. Hoyle studied how carbon, an essential element for life, is synthesized within stars. He discovered that the production of carbon depends on a very precise level of resonance in the nucleus of carbon. If this resonance level were slightly different, carbon would not form, and life could not exist. Hoyle commented on the famous phrase that the universe seemed like a custom-made job, suggesting it seemed designed for life. Since Hoyle's time, scientists have identified many other examples of fine-tuning. For example, the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces are delicately balanced. If the gravitational force were a little stronger, the stars would burn too fast for life to develop. If it were weaker, the stars might not ignite at all. The electromagnetic force, governing the chemistry of atoms and molecules, must also be adequate. If it were slightly different, the union of atoms would be impossible, and complex molecules essential for life could not form. The fine-tuning extends to the universe's initial conditions. The Big Bang, the event that birthed the universe, had to be incredibly precise. The universe's density had to be balanced to 1 part in 10 to the 60th power. To put it in perspective, like having a ruler that extends throughout the observable universe divided into increments of 1 inch, and the initial density of the universe had to be correct in 1 part in 1. If it deviated by that minuscule amount, the universe would have collapsed on itself or expanded too fast for galaxies, stars, and planets to form. One of the most striking examples of fine-tuning is the cosmological constant, which drives the universe's accelerated expansion. The value of this constant is extraordinarily small, yet different from zero. If it were much larger, the universe would have expanded too fast for galaxies to form. If it were negative, the universe would have collapsed into a singularity. The value of the cosmological constant is adjusted with a precision of approximately 1 part in 10 raised to 120, a level of precision that exceeds the imagination. So, why is the universe configured with such precision to sustain life? One explanation is the anthropic principle, stating that we observe the precisely adjusted universe, because if it were not, we would not be here to observe it. In other words, the universe must have the properties necessary for life, because we are here to perceive them. This idea began to take shape in the mid-20th century, when physicists and cosmologists began to grapple with puzzling observations about how finely tuned several fundamental constants and quantities of the universe seemed to be. One of the key figures in the development of the anthropic principle was the physicist Robert Dicke, who in the 1960s argued that the conditions that we observe in the universe must be compatible with the existence of observers. This line of thought was later formalized by Brandon Carter, a British physicist, in 1973. Carter introduced the anthropic principle during a conference that celebrated the 500th anniversary of CERN. He proposed 2 forms: the weak and strong anthropic principles. The weak anthropic principle suggests that we must consider the fact that our location in the universe is necessarily privileged to the extent that it is compatible with our existence as observers. In other words, the laws and constants of the universe seem adjusted for life because, if they were not, we would not be here to observe. This principle is largely observational and does not imply anything beyond the fact that we exist in a universe allowing us to exist. The strong anthropic principle, on the other hand, goes one step further. It suggests that the universe must have properties that inevitably lead to the development of intelligent life. This version implies a kind of necessity or purpose in the conditions allowing life in the universe. Some interpretations of the strong anthropic principle even suggest that the universe is somehow obligated to develop life and create observers. One way to think about the anthropic principle is to imagine a lottery with an astronomical number of tickets. The fact that you have the winning ticket means that, of all possible results, the one that allowed you to win is what you experienced. Similarly, of all the possible ways a universe could be configured, we find ourselves in one that sustains life, because only such a universe could contain observers like us. The anthropic principle has aroused much debate and discussion among scientists and philosophers. One of the main points of controversy is whether it provides a satisfactory explanation for the fine-tuning of the universe or whether it simply states the obvious, that we observe a universe conducive to life because we are here. However, critics argue that it does not really explain why the universe has these properties, but simply restates the question. On the other hand, defenders of the anthropic principle argue that it offers a useful framework for understanding why the universe is as it is. It aligns with the multiverse theory, which postulates that there could be a large number of universes, each with different physical laws and constants. Most of these universes would not be suitable for life, but we find ourselves in one that is. In this context, the anthropic principle provides a lens through which we can make sense of fine-tuning without invoking a higher purpose or design. The history of the idea of the multiverse goes back to various sources. One of the earliest forms of the multiverse was suggested by the many-worlds interpretation of quantum mechanics proposed by physicist Hugh Everett III in 1957. The Everett interpretation postulates that all possible results of quantum measurements actually occur in separate, branching universes. This was a radical break with the traditional view and laid the groundwork for thinking about multiple universes. The notion of the multiverse was further developed in the context of inflationary cosmology in the early 1980s. Physicists Alan Guth, Andre Linde, and others proposed the theory of cosmic inflation, which postulates a rapid exponential expansion of the universe shortly after the Big Bang. This inflationary period could create vast regions of space that are causally disconnected from each other, effectively forming separate parallel universes with their own distinctive properties. Linda, in particular, became a prominent advocate of the multiverse, suggesting that eternal inflation could give rise to an infinite number of these parallel universes. Supporters of the multiverse theory argue that it elegantly solves the problem of fine-tuning. If there are countless universes with varying laws and constants, it is not surprising that at least one has the right conditions for life. We exist in that universe because it is one of the few in which life is possible. This shifts the question from why is our universe adjusted for life to how many other universes exist. However, critics raise important objections to the multiverse theory. One of the main criticisms is that it is inherently impossible to prove by definition. The other universes in the multiverse are causally disconnected from ours, which means we cannot interact with or observe them. This makes the theory difficult, if not impossible, to verify through empirical tests, which are the cornerstone of the scientific method. Some critics argue that this relegates the multiverse to the realm of philosophy rather than science. Despite these criticisms, the multiverse theory has provided profound insights and stimulated considerable research and debate. It challenges our understanding of reality and expands the limits of what we consider possible. It also fits with other advanced theories of physics, such as string theory, which suggests that the fundamental components of the universe are not point particles, but tiny vibrating strings. String theory, with its complex mathematical framework and additional dimensions, provides fertile ground for multiverse concepts. It suggests that different ways of compacting these additional dimensions could lead to different physical laws and constants, potentially leading to a multiverse. As researchers delve into string theory, they discover more about its implications for the nature of reality and the possible existence of multiple universes. String theory is one of the most fascinating and ambitious theories in modern physics. It offers a possible theory of everything that aims to unify all the fundamental forces of nature into a single framework. At its core, string theory proposes that the most elementary components of the universe are not point particles, as traditionally thought, but tiny one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the particles and forces we observe. The origins of string theory date back to the late 1960s, when physicists were trying to understand a strong nuclear force that holds atomic nuclei together. Initially, string theory was developed to explain certain properties of hadrons, the particles that make up protons and neutrons. However, it soon became clear that the theory had much deeper implications. Beyond describing the strong force, in the 1980s, it evolved into a possible framework for unifying all fundamental interactions, including gravity, which had eluded a quantum description for decades. The most striking implication of string theory is the need for extra dimensions. While we experience the world in 3 spatial dimensions and 1 time dimension, string theory requires additional spatial dimensions, up to 10 or even 11 in some versions. These additional dimensions are compacted, meaning they are rolled up so tightly as to be imperceptible at our macroscopic scale. The idea of additional dimensions may seem strange, but it helps to solve many problems of theoretical physics, including the famous question of quantum gravity. String theory also offers an interesting way to explain the universe's fine-tuning. According to the theory, the way these extra dimensions are compacted determines the physical laws and constants of our universe. This leads to the concept of the string landscape, a vast range of possible configurations, each of which corresponds to a different universe with its own unique set of physical constants. If there is a multitude of possible universes, the fact that we find ourselves in one that is finely tuned for life could simply be a matter of statistical probability. From among the potentially vast number of universes in the string landscape, at least a few would have the right conditions for life to arise. Despite its elegance, potential, string theory is not without its controversy. One of the main criticisms is a lack of empirical evidence. So far, string theory remains a highly mathematical construction without any direct experimental confirmation. This has led some physicists to question whether it is truly a scientific theory in the traditional sense, since it cannot currently be tested or refuted by experiment. The theory's mathematical complexity also makes it hard to derive clear, testable predictions. Another point of controversy is the large number of possible solutions in the string landscape. While this could explain fine-tuning, it also raises the question of predictability. If there are so many universes, how can we determine which corresponds to ours? This challenge has led to debates about the philosophical implications of the theory and whether it will ever be able to provide definitive answers about the nature of our universe. As we explore the limits of string theory and reflect on the intricate dance of vibrating strings that may reveal the secrets of the cosmos, we are faced with even deeper questions about the nature of reality itself. One of these ideas that has gained adherence in scientific and philosophical circles is the simulation hypothesis, a theory suggesting our universe could be a sophisticated computer simulation created by an advanced civilization. The simulation hypothesis postulates that what we perceive as reality is, in fact, an artificial construction similar to a computer-generated environment in an advanced virtual reality game. This idea, although seemingly far-fetched at first glance, has a surprisingly solid basis in philosophical speculation and technological advancement. The concept was popularized in 2003 by philosopher Nick Bostrom, who presented a trilemma in his article, "Are You Living in a Computer Simulation?" Bostrom argued that at least one of the following propositions had to be true. Either almost all civilizations with our level of technological development become extinct before being able to create simulations of their ancestors, or if they reach that stage, they're not interested in carrying out such simulations, or we're almost certainly living in a simulation. The first part of the hypothesis, which explains it in detail, suggests that if an advanced civilization possesses immense computing power, it could be capable of simulating entire universes with conscious beings who are unaware that they are living in a simulation. These simulated beings would have experiences indistinguishable from those of beings in a real universe. The idea is based on the rapid advancement of technology, especially in fields like artificial intelligence and virtual reality. As our own capabilities to create virtual worlds continue to grow, the leap to imagine entire simulated universes does not seem so far-fetched now. Proponents of the simulation hypothesis argue that the computational resources needed to simulate a universe may not be as prohibitive as they seem at first glance. If we assume advanced civilizations have harnessed technologies far superior to our current knowledge, the idea of simulating not only a planet or a galaxy, but an entire universe becomes conceivable. They point to the exponential growth of computing power and the potential of future advances in quantum computing as evidence that such simulations might be possible. On the other hand, critics of the simulation hypothesis raise several important objections. One of the main criticisms is the lack of empirical evidence. Unlike theories of physics, such as string theory that can be explored through complex mathematical models, the simulation hypothesis remains largely speculative. There is currently no way to test or refute the idea that we live in a simulation, which has led some to dismiss it as an interesting philosophical exercise rather than a serious scientific theory. Another argument against the simulation hypothesis is the problem of the base reality. If our universe is a simulation, what about the universe of the beings who created it? Do they also live in a simulation? This leads to an infinite regress, in which each simulated universe could contain its own simulated universes, and so forth. This complexity raises questions about the probability and feasibility of an original base reality existing somewhere in the chain. Philosophically, the simulation hypothesis has profound implications for our understanding of reality. If we are living in a simulation, this challenges our notions of existence, consciousness, and the nature of the universe. It raises questions about freedom, the meaning of life, and our place in the cosmos. The fine-tuning of the universe, often cited as evidence of intelligent design or multiverse theories, could be explained as parameters set by the creators of the simulation to ensure its stability and functionality. One of the most intriguing aspects of the simulation hypothesis is its potential to unite diverse theories and observations that currently seem incompatible. For example, the seemingly arbitrary constants of physics could be the result of choices made by the simulators. The strange behaviors observed in quantum mechanics, such as the fact that particles are in multiple states at once, could be understood as limitations or characteristics of the computational framework of the simulation. Just as string theory breaks our understanding with the notion of hidden dimensions and multiple universes, the simulation hypothesis dares us to consider that our entire reality could be an intricate, artificial construction. But who is the mind behind this elaborate design? This question leads us to the concept of intelligent design, a theory suggesting that the universe and living organisms are better explained by an intelligent cause than by undirected processes like natural selection. The theory of intelligent design is based on the central idea that certain characteristics of the universe and living beings are better explained by an intelligent cause. This concept is based on the perceived deficiencies of naturalistic explanations, particularly Darwinian evolution, to account for the complexity and functionality observed in biological systems. Proponents of this theory argue that natural selection, random mutations, and other evolutionary mechanisms fail to explain the intricate details of cellular structures, the information-rich sequences of DNA, and the finely tuned constants of the cosmos. Historically, the roots of intelligent design go back to ancient philosophical thought. In ancient Greece, philosophers such as Plato and Aristotle contemplated the existence of an intentional order in the universe, laying the foundation for later arguments favoring design. Plato, in his dialogues, particularly in the Timon, introduced the idea of a demiurge, a divine craftsman who gives form to the cosmos according to an intelligible plan. This demiurge did not create matter from nothing, but ordered pre-existing chaotic matter into the structured universe we observe. The demiurge of Plato is a benevolent figure that intends to create a cosmos that reflects order, harmony, and purpose, reflecting the ideal forms that are perfect and immutable archetypes that exist in a non-physical realm. Aristotle, Plato's student, departed from his teacher by emphasizing empirical observation and logical deduction in his work, Metaphysics. Aristotle proposed the concept of the unmoved mover, an essential principle that causes movement and change in the universe without being moved itself. This unmoved mover, which Aristotle equated with God, is pure actuality, devoid of potentiality, and serves as the ultimate cause of all change and movement. Unlike the demiurge of Plato, the immobile engine of Aristotle is not a creator in the sense of actively designing the universe, but rather an eternal and immutable principle that imparts purpose and direction to all things. This idea laid the foundation for later arguments that perceived purpose and direction in the natural world as indicators of intelligent design. In the Middle Ages, Christian theologians and philosophers took these classical notions and integrated them into a theological framework reconciling faith with reason. St. Augustine of Hippo, an early father of the Church, integrated Platonic ideas into Christian doctrine. Augustine believed that God's creation was inherently good and purposeful, reflecting divine order and rationality. He saw the patterns and regularities of nature as manifestations of God's eternal ideas, existing in the divine intellect, an interpretation resonating with Plato's realm of forms. The most influential figure in the medieval synthesis of classical philosophy and Christian theology was undoubtedly Thomas Aquinas. In his monumental work, Summa Theologica, Aquinas systematically presented arguments favoring the existence of God, including the famous 5 ways. Among these, the fifth, known as the teleological or design argument, is significantly important in the context of intelligent design theory. The teleological argument posits that the natural order and purposeful behavior observed in the world suggest the presence of an intelligent designer. This reasoning is based on the observation that inanimate objects, lacking intelligence, act with an end or purpose. Aquinas argued that this purposeful action implies the guidance of an intelligent being. Aquinas pointed out that many natural phenomena exhibit regularity and order not attributable to chance. For example, the way planets orbit the sun, the intricate structure of living organisms, and the complex ecosystems in nature all point to intentional arrangement. Aquinas believed that such order and directionality in the natural world indicate a superior intelligence orchestrating these processes. One of Aquinas' key observations was that inanimate objects, inherently lacking consciousness or intelligence, act in ways achieving specific goals. For example, a seed that grows into a plant, the gravitational force of the earth that keeps objects on the ground, or the regularity of the seasons. All of these are examples in which non-intelligent entities work coherently to obtain specific results. Aquinas argued that, since these objects cannot direct themselves towards an end, there must be an external intelligent force guiding them. Aquinas' teleological argument is an adaptation of the Aristotelian concept of final cause or telos. Aristotle identified four causes: material, formal, efficient, and final, which explain why something is as it is. The final cause or purpose of something was fundamental to understanding its existence and behavior. Aquinas took this idea and integrated it with a theological perspective, postulating that the final cause is ultimately directed by God, the supreme intelligent designer. Music, according to Aristotle, everything in nature has a purpose or ultimate goal. For example, the final cause of an acorn is to become an oak tree. This concept of inherent purpose was fundamental to his understanding of the natural world. Aquinas started from this to argue that the final cause observed in nature is not self-sufficient, but requires an intelligent designer to set it in motion and guide it. For Aquinas, the teleological argument had profound theological implications by identifying God as the ultimate designer. Aquinas provided a rational basis for belief in an intelligent and purposeful creator. Intelligent. This argument supported the idea that faith and reason are not mutually exclusive, but complementary. It suggested that the natural world, when observed and analyzed, reveals the existence and attributes of God. Aquinas' argument implies that the complexity and order of the universe are not the product of chance, but deliberate design. God, as the ultimate designer, is responsible for the purposeful direction of all natural processes. This vision not only reinforces the belief in the existence of God, but also in his omniscience and omnipotence. By observing the natural world, one could infer the intelligence and power of the Creator. During the Renaissance and the Enlightenment, the design argument continued to evolve, adapting to new scientific discoveries and intellectual currents. The scientific revolution, with figures like Galileo and Newton, revealed a universe governed by precise mathematical laws. Many of these early scientists were devout Christians who saw their work as discovering the divine order of creation. Isaac Newton, for example, saw the intricate laws of motion and universal gravitation as evidence of a rational designer. The design argument reached its zenith in the 18th century with William Paley. Paley, an English clergyman and philosopher, in his work Natural Theology, compared the complexity of living organisms to a watch, arguing that just as the intricate design of a watch implies the existence of a watchmaker, so the complexity of nature implies the existence of a divine designer. Paley's watchmaker analogy became a central pillar of the teleological argument, emphasizing the apparent purpose and order in biological systems as evidence of intelligent design. However, the arrival of Darwinian evolution in the 19th century posed significant challenges to the design argument, which had long been used to affirm the need for an intelligent designer for the creation of complex life forms. The argument of the design, rooted in the idea that the complexity and the order in the nature suggest a creator with a purpose, faced a change of paradigm with the introduction of the revolutionary theory of the natural selection. The theory of the natural selection of Darwin provided a naturalist explanation of the complexity and the diversity of the life. According to this theory, species evolve through gradual changes driven by environmental pressures and genetic variation. In essence, organisms with traits better suited to their environment are more likely to survive and reproduce, passing those advantageous traits to future generations. Over long periods, this process leads to the emergence of new species and the adaptation of organisms to their habitats. This revolutionary idea undermined the need to resort to an intelligent designer to explain biological complexity. Before Darwin, many scientists and theologians saw the intricate structures and functions of the living organisms as proof of a deliberate design on the part of superior power. However, natural selection demonstrated that complex characteristics could arise from simple origins through a process that did not require conscious intervention. The ideas of Darwin, detailed in his influential book of 1859, The Origin of the Species, provided a naturalist explanation of the complexity and the diversity of a life. According to this theory, species evolve through gradual changes driven by environmental pressures and genetic variation. In essence, the organisms with more suitable traits to their environment have more probabilities of surviving and reproducing, transmitting those advantageous traits to the future generations throughout long periods of time. This process leads to the appearance of new species and the adaptation of organisms to their habitats. This revolutionary idea undermined the need to resort to an intelligent designer to explain biological complexity. Before Darwin, many scientists and theologians, following the reasoning of Pauli, saw the intricate structures and functions of the living organisms as proof of a deliberate design on the part of superior power. However, natural selection demonstrated that complex characteristics could arise from simple origins through a process that did not require conscious intervention. This naturalist framework suggested that the apparent design in nature could be an emergent property of evolutionary processes instead of the product of a divine creator. The introduction of the Darwinian evolution gave rise to intense debates and to a re-evaluation of the argument of the design. The defenders of the evolution, like the biologist Thomas Henry Huxley, argued that the natural selection provided a robust and verifiable mechanism to explain the diversity of the life, making superfluous the idea of an intelligent designer. Huxley, known as the Bulldog of Darwin for his energetic defense of the theory of Darwin, emphasized the power of the natural selection to explain the complexity of the life without resorting to supernatural explanations. However, critics like biologist and geologist Louis Agassiz maintain that certain complex biological structures and systems could not be adequately explained by gradual evolutionary processes, arguing that these characteristics still pointed to a designer. In spite of the debates in course, the theory of evolution has provided a framework to see the universe as a whole, without invoking a divine being. It has driven scientists and philosophers to look for natural explanations for phenomena that before were attributed to supernatural forces, when demonstrating that the complexity and the order can arise from simple natural processes. Darwinian evolution has fostered a more secular understanding of the natural world. In this framework, the universe is seen as a dynamic system governed by natural laws and processes. The diversity of the life is the result of thousands of millions of years of evolutionary changes driven by the natural selection, the genetic drift, the mutation, and the genetic flow. This perspective emphasizes the interconnection of all living beings, highlighting shared ancestry and the common processes that unite the biological world. Furthermore, this naturalist worldview extends beyond biology to other scientific disciplines, fostering a comprehensive understanding of the cosmos. In physics, for example, the theory of the Big Bang provides a naturalist explanation of the origin of the universe, while in geology, the theory of plate tectonics explains the movement of the continents of the Earth and the formation of diverse geological characteristics. These scientific theories, like evolution, rely on natural laws and processes to explain complex phenomena without resorting to supernatural explanations. Expanding this framework, some scientists and philosophers have explored the idea of a Darwinian evolution of the universe. This concept applies evolutionary principles to the cosmos as a whole, suggesting that the universe and its fundamental properties may also be subject to a kind of natural selection. One such idea is the theory of cosmological natural selection proposed by theoretical physicist Lee Smolin. According to Smolin, new universes are born through black holes, and each new universe has slightly different physical constants. The universes with properties conducive to the formation of black holes would produce more descendants, what would give rise to a process of natural selection that would favor the universes capable of generating black holes. This cosmological perspective suggests that the fundamental constants of nature, like the force of gravity or the charge of the electron, could be adjusted not by design, but by a process of natural selection operating at a cosmic level. Just like the biological evolution explains the adaptation and the complexity of the life, the cosmological natural selection could explain the apparently adjusted properties of our universe. At present, the movement of the intelligent design has gained prominent defenders, among which are figures like William Dembski and Stephen Meyer. These figures have been at the vanguard of the configuration and promotion of the intelligent design as a serious competitor of the predominant theory of the evolution. Dembski, a mathematician and philosopher, developed the concept of specified complexity, which, according to him, is a distinctive hallmark of intelligent design. According to Dembski, specified complexity can be at the forefront of shaping and promoting intelligent design as a serious contender to the predominant theory of evolution. Dembski, a mathematician and philosopher, developed the concept of specified complexity, which, according to him, is a distinctive hallmark of intelligent design. According to Dembski, the specified complexity can be recognized when something is complex. That is to say, it is not easily reproducible by chance and is specified in the sense that it coincides with an independent pattern or fulfills a specific function. He uses this framework to argue that the naturalist processes by themselves are insufficient to explain the intricate and deliberate arrangements that are found in the biological systems. Stephen Meyer, philosopher of the science, has contributed more support to the argument of the intelligent design through his work on the content of information in the DNA. In his influential book Signature in the Cell, Meyer maintains that the digital code embedded in the DNA, a code that directs the assembly of the proteins necessary for the life, is better explained by an intelligent cause. Meyer argues that natural processes, like random mutation and natural selection, do not adequately explain the origin of this complex information. He postulates that the sudden appearance of great amounts of specific information at cellular level points to an intelligent source, in a very similar way to how a software program needs a programmer. The modern movement of the intelligent design, as it has been mentioned previously, did not arise from nothing, but emerged from a long tradition of the argument of the design that goes back to the ancient philosophers and theologians that saw tests of the design in the natural world. The Enlightenment and later scientific revolutions brought significant changes, but the argument persisted and evolved into its modern form, largely as a response to Darwinian evolution. Unlike the creationism that directly invokes the biblical account of the creation, the intelligent design strives to present itself as a scientific hypothesis, although it is one that introduces the designer. One of the critical ideas proposed by defenders of ID, like Michael B., is irreducible complexity. The biochemist B maintains that certain biological systems, like the bacterial flagellum, are composed of multiple interdependent parts that contribute to the system's basic function. He affirms that the elimination of any of these parts would cause the cessation of the functioning of the entire system, which suggests that said systems could not have evolved through successive slight modifications, as Darwinian evolution proposes. Instead, he maintains that these systems must have been designed as fully functional units from the start. Despite these claims, the scientific community has largely rejected intelligent design, arguing that it lacks empirical support and does not provide a verifiable framework for a scientifically valid theory. For a theory to be scientifically valid, It must make predictions that can be empirically verified and potentially be falsified. Critics point out that intelligent design does not offer specific predictions about biological phenomena that can be verified in a laboratory or the field. Instead, it often criticizes the supposed gaps or deficiencies of evolutionary theory without offering a solid alternative explanation based on empirical data. Furthermore, intelligent design is criticized for not adhering to methodological naturalism, the principle that scientific explanations must be based solely on natural causes. By postulating an intelligent designer who operates outside the scope of natural laws, intelligent design enters the terrain of the metaphysical, which is beyond the reach of scientific investigation. This makes its verification or falsification difficult, leading many scientists to consider it a form of pseudoscience rather than a legitimate scientific theory. From a philosophical point of view, intelligent design faces challenges, such as Occam's principle, which favors simpler explanations with fewer assumptions. The theory of evolution, which explains the diversity of life through natural mechanisms such as mutation, genetic drift, and natural selection, does not invoke an external designer and is therefore considered a more parsimonious explanation. Intelligent design, by introducing the concept of a designer, adds an additional non-observable layer to explaining biological complexity, which, according to detractors, is unnecessary and complicates our understanding of life, instead of clarifying it. The burden of proof is another important philosophical obstacle for intelligent design in scientific discourse. The burden of proof falls on those who propose a new theory. The defenders of intelligent design claim that the complexity of life requires a designer, but they have not provided sufficient empirical evidence to support this claim. Affirmation. A large part of the argumentation in favor of intelligent design focuses on criticizing the theory of evolution, instead of building a positive case in favor of design based on empirical investigation. The controversy around intelligent design has also played out in the legal and educational fields in the United States. The most notable case is Kitzmiller versus Dover Area School District in 2005, in which a federal judge ruled that intelligent design is not science, but a religious opinion. The sentence concluded that it is unconstitutional to teach intelligent design in the science classes of public schools, which reinforces the opinion that intelligent design lacks the scientific credibility and the empirical support necessary to form part of the science curriculum. However, even as the intelligent design movement moves forward, an intriguing enigma that is often not addressed continues to exist. The universe shows both a perfect adjustment and profound imperfections. On one hand, the constants of nature are calibrated with precision to allow the existence of life. From the exact force of gravity to the precise charge of the electron, the universe seems finely tuned to support complexity and consciousness. However, on the other hand, this perfection is tarnished by significant cosmic imperfections. The universe is full of chaotic phenomena, such as black holes, bursts of gamma rays, and supernovas that can destroy entire stellar systems. Furthermore, the vast expanses of empty space and the presence of dark matter and dark energy add layers of mystery and unpredictability. Music. If the universe is truly designed by an intelligent agent, why does it present such notable defects? This duality poses questions about the nature of the designer and the purpose behind the apparently imperfect aspects of the universe. Music. When we consider the immensity and complexity of the universe, it is tempting to think of it as a perfect entity, finely tuned and harmoniously balanced to sustain life and its innumerable phenomena. However, upon examining it more deeply, we find that the universe is plagued with imperfections and anomalies. These imperfections are not defects, but essential components that drive change, evolution, and the development of complexity. In this debate, we will explore why the universe is considered to be perfect through its imperfections, focusing on the role of dark matter and dark energy, the philosophical implications of imperfection, and how these elements give shape to our understanding and to our ethical considerations. Our current understanding of the universe includes a fascinating mixture of known and unknown components. Among the most enigmatic are dark matter and dark energy, which together constitute about 95% of the universe. Dark matter, which represents approximately 27% of the universe, is an invisible substance that does not emit, absorb, or reflect light. Its presence is deduced from its gravitational effects on visible matter, such as stars and galaxies. Dark energy, on the other hand, constitutes about 68% of the universe and is believed to be responsible for the universe's accelerated expansion. The distribution of dark matter and dark energy is far from uniform, giving rise to what could be perceived as an imperfect structure of the universe. Dark matter tends to group together, creating gravitational wells that help form galaxies and clusters of galaxies. This grouping is essential for the large-scale structure of the universe, since it provides the scaffolding on which visible matter accumulates. However, the exact nature of dark matter remains a mystery, and directly detecting it has proven an immense challenge. Various experiments and observatories, such as the Large Hadron Collider and the Vera C. Rubin Observatory, are dedicated to discovering its properties, but so far dark matter has eluded direct observation. Similarly, dark energy poses significant observational challenges. It is believed to be a property of space itself that causes the universe to expand at an ever-increasing rate. The distribution of dark energy is even less known than that of dark matter, and its exact nature is one of cosmology's greatest unknowns. The apparent imperfections in our understanding and the distribution of these components highlight the limits of our current models and the universe's complexity. These imperfections in the distribution of dark matter and dark energy have profound implications for cosmology, since they affect our models of the evolution of the universe and challenge our understanding of its ultimate destiny. For example, the problem of baryonic asymmetry, which refers to the imbalance between matter and antimatter in the universe, adds another layer of complexity. According to the Big Bang Theory, matter and antimatter should have been created in equal quantities, but we observe a universe dominated by matter with very little antimatter. This asymmetry is crucial for our existence, but it remains an unresolved enigma in cosmology. Although the universe's imperfections may initially seem like defects, they are actually essential to the dynamic processes that drive cosmic evolution. Let's imagine a universe where everything is perfectly balanced and uniform. Such a scenario would be disturbingly static, lacking the complexities and changes that define our cosmos. It is precisely these imperfections, these slight deviations from perfect symmetry, that fuel the rich tapestry of cosmic development. Let us consider the early universe shortly after the Big Bang, when it was a hot, dense, and almost uniform sea of particles. If it had been completely homogeneous, without variations in density or temperature, gravity would have nothing to act upon. There would be no denser regions for gravity to attract, no seeds for stars and galaxies to form. However, the universe was not perfectly uniform. Small quantum fluctuations in space-time created slight irregularities, regions a little denser than their surroundings. Over millions and billions of years, these denser regions attracted more matter through gravity, gradually growing into the stars and galaxies we see today. This concept of imperfection extends beyond the initial conditions of a universe. Take, for example, the formation of stars inside galaxies. The interstellar medium, the vast space between stars, is full of gas and dust, far from uniform. Clusters of gas, often disturbed by shock waves from supernovas, can collapse under gravity to form new stars. These stars, in turn, may have planets orbiting them, some of which may be in the habitable zone, where conditions are right for life as we know it. None of this would be possible in a perfectly uniform universe. Furthermore, these imperfections are not only physical, but temporal too. The universe is constantly evolving, with stars being born and dying, galaxies merging and interacting, and black holes growing and influencing their environments. Each of these events introduces new imperfections, new asymmetries that further drive complexity and evolution. The death of a star, for example, can lead to the creation of heavy elements essential for the formation of planets and life. Supernovas, the explosive deaths of massive stars, scatter these elements throughout the galaxy, enriching the interstellar medium and paving the way for new generations of stars and planets from a cosmological perspective. The irregular distribution of matter, the formation of galaxies, and the variations in cosmic background radiation are not simple random whims, but footprints of the history of the universe and its continuous evolution. The cosmic background radiation, for example, reveals slight temperature fluctuations that correspond to regions of varying density in the early universe. These density variations were crucial for the formation of galaxies, as gravitational forces caused matter to cluster over time, eventually forming the complex structures we observe today. Without these imperfections, the universe would be a homogeneous soup of particles, devoid of stars, planets, and life. In the natural world, imperfection is the basis for biological diversity and resilience. Genetic mutations, which could be considered errors in the replication process, are actually the raw material of evolution. These mutations introduce variability into populations, allowing organisms to adapt to changing environments. This adaptability is evident in phenomena such as antibiotic resistance in bacteria, where random mutations confer survival advantages under selective pressure. Environmental variations also play a crucial role in shaping ecosystems, creating diverse habitats that are home to a wide variety of species. For example, the different climates and terrains of the Earth, from arid deserts to lush rainforests, provide niches for different organisms to thrive and evolve. Adaptation and resilience are derived from these biological imperfections. Life on Earth has endured and flourished over billions of years of environmental change, from ice ages to asteroid impacts. This resilience is observed in the way plants and animals have developed mechanisms to cope with stress, repair damage, and take advantage of new opportunities. For example, the ability of certain plants to go dormant during droughts or the migratory patterns of birds in response to seasonal changes are examples of how life adapts to survive. These adaptations are a testament to the strength and creativity inherent in biological imperfections. Contemplating the imperfections of the universe also encourages us to recognize and address our cognitive and cultural biases. Our interpretations of cosmological data are influenced by our limited perspectives and inherent biases. By recognizing these biases, we can strive for more objective and accurate scientific research. Different cultures and philosophies offer diverse interpretations of the cosmos, reminding us that our understanding is shaped by our backgrounds and experiences. Embracing this diversity of thought enriches our scientific efforts and fosters greater acceptance of different points of view, leading to a more holistic understanding of the universe. Recognizing the fragility and rarity of life in the vast cosmos underscores its intrinsic value. Life, with its delicate balance and complexity, is an extraordinary phenomenon. This recognition compels us to appreciate and protect the conditions that allow life to thrive on Earth. This means taking action to address environmental challenges like climate change, habitat destruction, and pollution. In the broader context of the universe, it demands a respectful approach to space exploration, ensuring that our pursuit of knowledge does not damage potential ecosystems on other planets or moons. The ethical implications extend to our responsibility to nurture life wherever we find it, understanding that we are guardians not only of our planet, but also of other potential worlds. Therefore, the imperfections of the universe are not defects, but the very foundation of its dynamic nature. They challenge us to appreciate the complexity and beauty of existence, to strive to understand it more deeply, and to act with ethical consideration towards the world and the cosmos. These imperfections are the threads that weave the intricate and ever-changing tapestry of the universe, inviting us to reflect on our place in it and our responsibilities as inhabitants of this extraordinary realm. In our quest to understand the universe, we encounter the concept of fine-tuning, the extraordinary alignment of the physical constants and conditions that allow life as we know it. This speaks to us of a universe apparently created with meticulous precision, which fosters the conditions in which stars can form planets. These can sustain life, and complex beings can reflect on their own existence. This fine-tuning evokes a sensation of awe and wonder, suggesting a cosmic plan or a guiding hand behind the scenes. However, along with this apparent perfection, there is imperfection, irregularities, asymmetries, and unpredictability that permeate every corner of the cosmos, from chaotic collisions of galaxies to minute quantum fluctuations. These imperfections challenge our orderly theories and test our current understanding. They remind us that the universe is not static, but fluid, not predictable, but infinitely surprising. Looking ahead, human understanding of fine-tuning and imperfection has profound implications. Scientific discoveries continue to expand our knowledge, delving into the mysteries of physics, cosmology, and the origins of existence. Each revelation adds another layer to our understanding, but also reveals new questions that invite us to delve even further into the realms of exploration and research. In reflecting on these complexities, we are encouraged to not only marvel at the intricacies of the universe, but also engage in ethical reflection. Our awareness of tuning invites us to consider our stewardship of this planet and our responsibility to its preservation. At the same time, the recognition of imperfection humbles us before our scientific arrogance, reminding us of the limitations of our current knowledge and the immensity of what remains to be explored. In conclusion, the future of human knowledge lies in a delicate balance between accepting the wonders of fine-tuning and grappling with the enigmas of imperfection. This requires constant curiosity, rigorous investigation, and ethical awareness as we navigate the frontiers of knowledge. In doing so, we not only deepen our understanding of the universe, but also enrich our appreciation of our place in it, fostering a deeper connection with the cosmos and with each other.